Perfect, wonderful. So,
Yeah.
so now the recording is going. So welcome again, Professor Dustdar. And if you have any questions, feel free to send them via chat to me, and I'd be happy to relay them at the end of the talk. So without further ado, welcome.
Thank you very much, Carlos, for your kind introduction, and welcome everybody for joining. It's a great pleasure, privilege to be here. I see a lot of familiar faces. Hi, Massimo. Great to see you. So in this talk, I'm gonna present my perspective on how the edge and the fog and the cloud are related, and give it kind of a new spin with edge intelligence and how I look into this. And I would like to kind of have I will begin with a holistic view of the whole situation, and then I will come to a perspective which is a little bit particular, in a sense that I would like to draw your attention to an area of research where I believe that we all can collaborate in case you're interested. So let's begin to look into this area. So I think that we
like to. Can you please share your screen? Okay, it is there. Yeah.
Sorry.
Sorry for disturbing. I thought it is not shared, so it is view is different. Yeah. All good.
Yeah, you can see the screen, right?
Yeah, I can.
Yeah. All right. So I would like to begin with a general observation that we are in midst of a smart evolution of the systems that we are building. What I mean is that we are increasingly building systems which are composed out of three ingredients, namely people, software, services, and things. And this might sound trivial, but in fact, as we will see along the lines, this is not really trivial as it looks like. The systems examples are many. We can have, smart home systems, smart building systems. We can e-health systems, governmental systems, administration systems, even transportation, autonomous vehicles, etc., and energy network systems. All of these systems have these ingredients within them, however, to different degrees of emphasis on these three components. And in particular, as computer scientists, we have been focusing on the software services side, so to speak, and the things were not really of prime concern so far for computer science. They were mostly of concern, let's say, to networking people, maybe electrical engineers. And the people were really outside the core system concerns. I mean, we were concerned with people interacting with the systems, but not as functional building blocks of the system. Now, what I'm saying here is that the systems that we are building, I call them elastic systems for the lack of a better term, basically are composed out of these three building blocks, and these three entities are integrating with each other. And that is a huge challenge because the abstractions don't fit, the responsibilities, the messaging protocols, and all of that are really challenging for us to integrate. Now, we can see then that all of these three building blocks are actually connected with each other, right? So like in the big, it's also in the small, right? So when we have different components like people and the software services and the things, they all relate to each other. So whenever we have to design such systems, we have to be aware of this connection. So this is the underlying assumption of my presentation. So this underlying assumption also draws from an analogy from nature. So when we look at natural ecosystems, like in this picture here, the marine ecosystem, we can see that there is the sun, the birds, the rocks, the water, all the animals, etc., and they are actually interacting with each other. So we can say then that this is a complex system. It has networked dependencies. It has intrinsic adaptive behavior. And I think that this is something that we have to mimic in the systems that we are actually building. So we have to mimic these four types of features, so to speak, that we have to create. So the first one is robustness and resilience mechanisms. So we have the question, how to achieve stability in the presence of disruption. We have, secondly, measures of health of that system. So we can say something about the diversity, the population trends, and other key indicators. The system, the ecosystem has a built-in coherence. and it is also a resisting entropy typically. So this is what is called syntropy. So this can actually build itself to refresh itself and keep going. So what I would like to draw your attention are these yellow arrows, in fact, right? So these yellow arrows are the interactions between these building blocks. And similarly, my argument is that in our types of information systems that we are creating, these connections, these interactions are equally important. Now, when we map that to the world of distributed systems, we can say then that, you know, in nature, we have all these different building blocks. Similarly, we have that also in our distributed systems. We have compute power, network, we have different types of devices, all sorts of connections and the like. So when we map that into the current situation, we can say then that we have, for example, a smart city. In a smart city, we have many things, Internet of Things types of devices. We have sensors for fire, air, traffic, video, what have you. We have different software applications building on top of that for disaster management, traffic control, parking, watering services, smart facility and the like. We have us running around with our mobile phones in that city, and we are also leaving traces of data, right? So this is a representation of what I was talking about before, and we have that all the time in front of us. So we can then say that the actual core abstraction, as we have seen it in the last couple of years, is the everything as a service abstraction, right? So all of these can build as an abstraction and being connected with each other. So the first observation then is that we have a new family of applications that are coming to the foreground, namely that they have real-time location-based access to data from the environment at different levels of fidelity. So not all information systems have to have the highest fidelity or the highest granularity of the data available. For some applications, different levels are sufficient. Secondly, we have increasingly the requirement to have compute and storage resources in closer proximity to the data producers and the consumers. Now, when we look into the current situation of the information systems world, I would like to kind of draw your attention to the problem, what I call the dynamic analytics problem. So when you take an example like COVID, for example, in the situation of COVID, what we are doing is we are looking at the mobility patterns of people. Then we are having simulations of trends, how things are developing. And we have maybe the general situation of social welfare, of healthcare data that we have, etc. And we try to integrate them by hand, more or less. The problem seems to be that the systems that we have created in the last 5 decades or so are actually built in isolation. What I mean is that they have been built in vertical domains, like for government services, well-being services, building management, etc. And then we have horizontal services, which are doing different things. However, all of the major problems of society in the next decades to come, including the climate change aspects, energy consumption, what have you, are actually all requiring to connect all of these different building blocks horizontally and vertically. So this is a huge challenge for us. And I think that in the past, we have created great systems which brought us to a certain level of complexity. But as you look at this situation right now, there are so many different building blocks we have to constantly connect that it is becoming a challenge, because it's not really an integrated system. It is not really an integrated infrastructure, right? So everything that we are doing essentially is always patching different building blocks together. And I think, and this is my core assumption here, is that this is increasingly becoming a fundamental problem. Now, if you look at different perspectives on this distributed systems infrastructure, there are basically two major threads we can look at. The first one is, which has been or has become the dominant assumption is that the cloud is the center of everything. So it's what I call the cloud-centric perspective. And everything around it is actually connecting to the cloud. Second is the internet-centric perspective, where we see the internet as the main kind of building block connecting everything together. The cloud is connected, the things are connected, the edges are connected, etc. And actually, as primitive as it looks like, most of the awareness has gone in the last years to the cloud as the center of everything that we are doing. So much so that the edges and the IoT and the people are actually, you could say, they cannot be operated properly without the cloud. And what I'm saying here is that this is actually a problem. It would be as our body could not function if not everything is done consciously from the brain, so to speak, which is not true. We have the autonomic nervous system, we have the heart. The heart has also 40,000 neurons. So there is a lot of stuff going on, decentralized and distributed as well. And similarly, my claim is that we have to mimic that behavior in order to create larger scale distributed systems infrastructures to be successful. Now we map that onto a structure that we are seeing in current information systems. So the current
Schahram, 1 second. Sorry for the interruption.
Sure.
There is a point that there is a big black space around the slides, and there was a question whether it would be possible to somehow make the slides look larger in the screen, if that is possible.
I tried it, but I'm not sure. It did not work in the past, so that's why I didn't want to. I don't know. I created it in a big way. So but you can see it.
Yeah, I think there is a big black frame surrounding the slides.
Okay. Yeah, I don't want to disturb the flow.
No, let's keep going then. Let's keep going.
Yeah.
You can see. So.
You can see. I can share the slides also. It's not a problem. So basically, what I'm saying is that we look into this whole infrastructure building blocks in front of us. We can see the IoT, the edge, the fog, and the cloud. And what I'm saying here is that actually this is a whole continuum of compute infrastructure, right? And they have different properties, as you all know. On the left-hand side, we have the IoT world and the sensor world, and the edges maybe. We have low reliability, high volatility, mobility, small form factors, battery constraints, etc. And typically those devices are controlled by users, maybe increasingly in the future with service providers. As we move to the right-hand side, we have the edge devices, the edge compute nodes, where we have low latency to the end devices. They are closer or maybe co-located to base stations from telcos, general purpose compute infrastructure, sometimes operated by telcos, sometimes operated by companies. As we move to the right, we can see more telco operated equipment like fog devices with the base stations, which are part of the core network and connected to the internet. And on the right-hand side, we have what we all know very well is the cloud domain with the under quotes unlimited compute and storage resources, the full spectrum of what we have. Cloud provided and controlled. Now, the problem is, if you look at these infrastructure as a whole, application developers, infrastructure providers, companies, developers, etc., all of the stakeholders involved in this have the problem of determining where should the applications actually be deployed. How is the management going on this overall large infrastructure? How are the businesses actually sharing revenues, right? So a big part of the future will be revenue sharing, bandwidth sharing, band sharing between the telcos, etc. But there are many problems from the technical side, protocol side, and business side, if you look at it from the whole continuum. So this is where I would like to draw your attention to, basically looking at this whole perspective of this infrastructure. So if we abstract from that, we can basically say it becomes a question of horizontal and vertical offloading, so to speak. it's not only offloading in the sense that it's very kind of granular and you can offload things here and there, but the question is really the emphasis horizontally and vertically of the communications and coordination of the different players in what we are doing. So this whole compute continuum horizontally and vertically is quite a huge continuum. You have from data center to mini servers to micro clouds, as you see on the right-hand side, being weaved together, right? And this is actually quite a challenge for us to put together these different infrastructure components. Now spice that a little bit with specialized compute platforms such as AI, a specialized sticks like the Intel stick or NVIDIA Jetson cards or Huawei Atlas cards and stuff like that, which have special AI capabilities and which are enriching actually the infrastructure that we have. The question becomes for us, is it possible to write the applications, the services once and run it everywhere? This is necessary because we have city scale infrastructure really. So we have it from the small to the very big, like the Polestar examples in the cities, which are actually bringing together all of these different examples that I'm talking about. So my pitch basically is that we have, in order to manage such systems, we have to look at it not from a things perspective only, like we did in the past, and connect the things directly to the cloud and have this interaction going on. But we have to become aware that this is a software intensive edge systems game, where we have to totally rethink basically the design and the operation of such environments. And we have to deal with it in a way that has to manage conflicting systems factors. What I mean is that we have different systems factors which we have to trade off, right? So we have latency. So there is this inherent traditional division of the cloud and the IoT, which definitely affects everything from time, performance, etc., and which has been used as an argument for edge systems. Secondly, the computational aspect as an edge resource, right? Increasing safety potentially and security because we can distribute it as well. And thirdly, locality and mobility is becoming increasingly important because these privacy aspects coming from the computation on the edge is helping privacy in principle, if we do it correctly. And that's a big issue, how to correctly do these things, right? Issues of software configuration and evolution of the systems is becoming, again, of prime concern. So as you see that there are many different types of questions which are related to the question of, if we kind of see that from a software perspective, many things become truly interesting as well. So the question is, which characteristics of edge computing systems should be actually abstracted as first-class citizens into the underpinning models that we use, the programming models, the abstractions that we are using for us to design, develop, deploy, and govern such systems? One hypothesis would be that we have to take into account proximity of the devices, the context of the overall compute infrastructure, the capabilities and the energy, etc. But in this talk, I would like to basically focus on one aspect, which is what I call elastic diffusion. So this is one kind of perspective I would like to add here, so that I would suggest to look at this problem from the question of how elastic is a system and how can it diffuse what it needs to diffuse overall in this infrastructure. What do I mean with elasticity? Elasticity on the principle level is a property in material science from physics, which says something about a property returning to an initial form or a state following some deformation, right? So you put stress on a material, it deforms. If you take away that stress, it goes back to its initial form. This, in principle, increases the resilience. Now, we all know since a decade or so, at least, we are talking about elasticity in the context of cloud systems, right? And predominantly, when we look into elasticity, we speak about resources. The claim here I have is that elasticity is not only confined to the question of resources utilized, it's actually a very deep and rich area of concern. What do I mean? When we create typically elastic systems in a traditional sense, on the quotes, we build actually scalable systems, which are able to scale from the resource perspective. What I would like to propose, and I'm working on since many years, is basically looking at this problem not only from the resource side, but actually adding additional dimensions. And these additional dimensions are, on top of resources, two orthogonal dimensions. One is the quality aspect, all the non-functional parameters that we have, like the quality of the data input and output, which is important. And thirdly, the cost elasticity, right? So how much does it actually cost? And my fundamental assumption is here that for all types of systems that we are building now, we are constantly operating in this three-dimensional space of creating applications which are trading off resources, the quality of the data input and output, and the cost at the same time. And this wasn't necessarily so in the past. We had a bunch of resources and we just built the systems that made sense for the worst case, basically. Maximum number of users, available bandwidth, and the like. Now, what I'm suggesting here is that we should take this as a trade-off model, look into the quality of data input and output as an example, and also cost, and make those also first-class citizens, so to speak, so that the applications that we are creating are actually operating in this three-dimensional space. We have done a number of research projects in the past, and are also currently doing that, where we created a language, descriptive language called Sybil, which is exampled here. This example is for the cloud, where we have a language which allows the designer to attach elasticity constraints and requirements to different levels of abstraction, to the cloud service, to the service unit level, but even to code which you have no service abstraction for. And the system overall created the mechanisms, the monitoring, the change that is necessary in order to balance the system out on these virtual machines represented as these green puzzle pieces here. And whenever the constraints of this elasticity are not met, which are specified on the left-hand side, the system itself rearranges where the deployment, for example, is being done. So for example, you could define a strategy saying, I always want to have maximum data freshness, but only if the cost is less than €3. You don't want to, you don't want to have fresh data at all costs. Definitely, this is a good requirement, right, to put in, right? And you can do that with all sorts of different aspects represented here. You have your own imagination. The point is that we have a language where we can actually specify these elasticity requirements, as we call it, on the different pieces of the software services which do certain things. What does this mean for looking at it from the holistic perspective on the application landscape? This means that basically we can say, and we can look at an application as it evolves over time. The application is operating in this three-dimensional space. That's why this triangle, it has resources, it has quality, and it has cost. So these are the three dimensions of the applications. And the elasticity space is represented by these orange boundaries on top and the bottom. It basically says that, is my application within this elasticity behavior that I have specified, right? The other perspective that you can look at it is what I call the elasticity pathway. It basically looks at it, is the application evolving over time, and at what points in this workflow, so to speak, am I losing money? Is the number of resources too high? Is the cost too high? Is the quality bad or good, etc.? So this perspective allows basically a different view on applications that we are creating. The second aspect I want to talk about, and I have some collaborators here, is the diffusion aspect. Also what we call it osmotic computing. Osmosis is a concept from chemistry, as you know. It represents the diffusion from molecules from a higher to a lower concentration. And it creates pressure in a sense. And whenever that pressure is at a certain threshold, the molecules start to wander to a lower concentration. So in other words, we have a homeostasis of the overall liquid here. And there are membranes, etc. So we thought that it would be a good kind of concept to visualize, to conceptualize what this would actually mean for the world of elasticity and edge and cloud and IoT. So this would mean for us that we look at a system and the software services being deployed not only on one particular sort of compute device, such as cloud data center, etc., but actually also along this continuum as we are speaking. So these parts of the system should be deployable on edge infrastructures, on cloud infrastructures, on fog base stations, what have you. And the question is, can these software services, which do a certain functionality from serverless to cloud, basically, if you like, can they wander around similar to this diffusion of molecules without us as the designers of the system constantly saying explicitly where to go? In other words, is it possible to bring in the intelligence of what is needed into the system infrastructure itself? And our claim is somehow that this should be possible. However, it is a requirement that we basically specify more information about the requirements regarding these three-dimensional elasticity spaces, that's for sure. Because if we have that, we can basically reason much better where things should be deployed, how it should be managed, how much does it cost, etc. So this brings me to the last part of this presentation, namely to focus now on the intelligence, on the quotes aspect of this. So I was emphasizing this elastic diffusion because I think this is the glue or the paradigm, if you like, or the one of the concepts that are necessary first to comprehend and understand before you can actually talk about intelligence and shifting that intelligence to the infrastructure itself. And this is what I call here, and many people call edge intelligence. So in other words, how does a computational fabric look like where we have a dispersed set of resources, training, monitoring, and serving these models? And where are these intelligence operations, these mechanisms that are required to actually deal with the whole scale of such an infrastructure? And how is it possible to create an automated AI application lifecycle management, which goes also down to the edges of the network? Because ultimately, we have to use and utilize the whole compute continuum from the edges of the network to the cloud. So far, predominantly in the last decade, we have focused on the cloud. Everything was happening on the cloud. The whole magic sauce, basically, as I call it, is happening on the cloud, the machine learning, the models, the reasoning, etc. But as we see that, this is now becoming, again, the decade of distribution and decentralization. So it's much more fun for us researchers, I would say. We have to look at it from that perspective, right? So this fabric for edge intelligence basically has a number of ingredients which is worthwhile to look at. The first one is sensor data as a service, the sensing aspect. So we have a large number of dynamic and mobile publishers, subscribers. So we have to rethink these centralized messaging services like Amazon Web Service IoT or Microsoft Azure IoT Hub, etc. So we move towards a management and governance of a distributed decentralized sensing infrastructure. Secondly, these edge computing devices and networks increasingly have modular AI capabilities, as I was indicating before, right? In the small sense, we even have these little devices which we can put on top of this, even Raspberry Pis, etc., down up to the bigger devices that we have, GPU servers, what have you, equipped with particular hardware devices to do more AI in a faster way. And thirdly, of course, the whole intelligent orchestration mechanisms for this decentralized and distributed infrastructure. So these aspects are truly fundamental for these edge intelligence considerations that we have to do. And we have played around with what is possible for us as a university institute to look into create general purpose computing infrastructure, equip that with like embedded AI hardware, and play around with it like what we show here, where we can basically shift jobs based on different energy consumption requirements that we have specified, similar to what I was showing to you before, and train the middleware, which is basically then AI kind of trained, and shift workloads to these different parts of the compute infrastructure. And some of them are listed here as papers, and many more can be found on our homepage. So if we look at this now from a learning perspective, of course, federated learning in distributed systems has been around for some time, and I want to kind of refresh what is actually required here. So the training on data is directly done on remote devices without revealing the data itself. It is sending outcome of local training to a server, wherever that server resides. The server aggregates these updates into a global model and makes those models available to the devices. Now the question becomes, where does this magic actually happen? And one of the fundamental assumptions in this work is that this is being shifted from the centralized cloud, more or less, downstream to multiple layers of edge devices, fog devices, etc. And from a business side, many players are involved in this, from telco-operated fog and edge devices, down state base stations, for example, down to edge devices which are operated and controlled by individuals, by ISP, by corporations and such. So the problem becomes really fundamental for us to address. There are many types of applications in the mobile world. We have face detection, voice recognition, where you want to train on the data from a smartphone, for example, or a microphone, a camera, but you don't want to reveal the message or the photo or the video itself. Same is true for organizations. You have hospitals, for example, they have the data, but they don't want to expose them. You have the same for environment, transportation, smart home, buildings, etc., where you have different types of devices sending, streaming data, air pollution, etc., down to smart homes, etc. So there are multiple applications increasingly putting an emphasis on this type of infrastructure and intelligence that would be required us to do. In a way, it reminds me of our own human body, where everything is connected with each other. We have built-in thresholds like blood pressure, heart rate variability, and all these things. We can measure them, and if they are not working seamlessly, things go wrong, right? So similarly, we have to create the applications, the infrastructure that we are creating in a way that there is a seamless diffusion between everything that we are doing. That's why I put some emphasis on this elastic diffusion. There are many research challenges, so it gives us enough work to do. The question are, some of them are listed here. Okay, so how do I recruit the devices? So which devices actually do these learning tasks at any given round? Many of them are available, maybe not all are chosen to provide the data. It is highly volatile. The devices can appear, disappear at any point in time. Asynchrony challenges, so these algorithms, they face challenges when end devices don't submit their data in a timely manner. We have non-independent and identically distributed data, so personalization is lost, it might be inaccurate. We have heterogeneity in the volume of training data per device. So a device that contributes a lot may lead to a biased model. So we have the same problem that we have in social networks, that things might become an echo chamber. We have that also in the world of devices. We have to look into privacy and the potential privacy leaks. So private information may be inferred even if the device doesn't transmit the data itself. And we have also incentives to misbehave overall. So like, why should I waste my battery in my device when I can let others do the work? So there are lots of research challenges in front of us. So when we look into these research challenges, we created a research roadmap for the question of edge intelligence, where we actually put those into a kind of perspective and a structure and a proposal, so to speak, for everybody to be involved in this work. So we look at that from a quality of experience level. This means that we look at it from the end user perspective. First, what is it that the user experiences? That is what we call the quality of experience. And these are the 5 top things that the user experiences. Performance, of course, has an impact on the ratio of computation offloading. The cost, of course, where is the computation happening? Where is the communication happening? How? And the energy consumption. Privacy and security. So, as I said, the question of federated learning, aggregating local machine models from distributed edge devices. How do you do that? Efficiency, can I have excellent performance with a very low overhead? How can I compress these models? Can I do conditional computation? And reliability. So how can I do a model upload and download in wireless network, and if it's congested or poor network connection, etc. So these are fundamental questions related to the question of quality of experience. And then we basically mapped those onto 2 levels where we say, okay, there is AI involved in this space, AI for the edge and AI on the edge. And I want to discuss that briefly. Of course, more details you can find in the paper itself. So the AI for the edge looks into 3 questions. The first one is regarding topology. So the edge orchestration and coordination with these base stations I was talking about before, right? So like unmanned aerial vehicles and access point. How does the topology of the infrastructure actually look like? How should it change, if it should change? Secondly, the content. So I need to have lightweight service frameworks for this quality aware, service aware services, for example, on mobile devices or smaller form factor devices. Services, where do I do computational offloading? How do I do user profile migration, mobility management? There are multiple grand challenges in the area of AI for the edge. How do I establish these models? How do I restrain the optimization model? There is some related work in this space, but there are still a lot of work for us to do. Secondly, how do I do the algorithmic development? So how do I come up with a good algorithm to select which edge should actually be responsible for the deployment and the execution in an online manner? So the state-of-the-art formulates some combinatorial and NP hard optimization problem with high computational complexity. Can we do it better? That's a very practical issue. The trade-off between optimality and efficiency. So as we have many resource constraint devices, this becomes a fundamental problem of trade-offs as we speak, because we have constantly different devices involved with different capabilities. Then the other dimension is talking about AI on the edge, which has its own challenges, right? So the availability of data, because we have the challenge of a lack of availability and usability of the raw training data for model training and inference. And that leads ultimately to a bias of raw data from various end user mobile devices, which is a fundamental problem. The similar problem that we have in social media, right? A bias of data coming in, determining basically the fate of the application, if you like. The model selection. So the state of the art requires that we select the need to be trained AI model, and that has challenges in this type of infrastructure. The thresholds of learning accuracy and the scale of AI models and the quick deployment and delivery. How do we select the probe training frameworks and accelerator architectures under these limited resources? And thirdly, the coordination, the orchestration mechanisms between these different middlewares distributed on these infrastructures. So as you see, there are many different challenges in this aspect of the intelligence fabric. And finally, also the AI lifecycle as a general workflow, as a pipeline, which is pre-processing the data, creating the training, evaluating, deploying, creating these models, measuring the performance, etc. So this workflow in itself is and was always a challenge, and is now even amplified by this distributed and decentralized part of the infrastructure. And as the time is progressing, I just want to kind of highlight the operations workflow on different dimensions and put this table here. Basically, on the left-hand side, you can see cloud to cloud, cloud to edge, edge to cloud, and edge to edge perspectives regarding the data characteristics, the model characteristics, and the enabling technologies, and how to actually look into this problem. Provided also some use cases. So if you follow that paper, you can actually see the examples that we are given here. So this is a huge set of challenges in front of us if we want to create this highly decentralized and distributed infrastructure for edge intelligence. So this brings me to the conclusion. On a high level, we can say that one of the main tasks or understandings and learnings is that we have to leverage the whole compute continuum from the IoT sensor world over the edge to the fog to the cloud. And I'm emphasizing here the holistic perspective on the infrastructure as we speak, and the whole set of devices. Second learning is that we have to have an edge intelligence fabric and a clear ecosystem understanding. With that, I mean that everything is connected with everything. We have to transcend the previous isolated systems that we have built, because they simply will create more problems, right? So for example, climate change is a fundamental global problem. Food networks, food distribution is a fundamental problem increasingly. And we cannot address those types of problems simply by gluing and patching different systems together. So my proposal is to have this ecosystem understanding. And thirdly, very concretely for us researchers also, to differentiate between AI for the edge and AI on the edge, and looking into these research challenges in particular. So with that, I want to thank you very much for your attention, and I want to also look forward for any question that you have. Thanks very much.
Thank you very much, Schahram. So let me address, relay some of the questions. So Maximilian Engelsberger says the following: thanks for the talk. Where do you make the difference between osmotic computing and the paradigm of liquid computing from 2014, where data and services follow the user around different systems?
I'm not so familiar with the liquid computing aspect, not so familiar. I think that the emphasis that we are following with the question of osmotic computing is putting emphasis on the infrastructure level, really, and not so much on the application level. So individual applications or parts of applications, looking into okay, the data as the data aspect and the functionality aspect. My perspective on that is that the osmotic infrastructure, osmotic computing paradigm looks more on the infrastructure level and the fundamental issues, rather than the application specifics only.
And I actually have unmuted Maximilian, if you want to follow up. Okay, I guess he's fine. So one other question for AI on edge. This is from Dhritiman Mukherjee. For AI on edge, how can we deal with resource constraints?
Well, in that paper, actually, there is a list of questions that we have to look into. And as I said, also, I think that the question becomes of a trade-off. So we have to, so when we have resource constrained devices, they cannot do everything, and not everything for in a certain time and in a certain cost and quality consideration, right? So we have to become aware of this. And this means that we have to take into account all these different parts of the infrastructure and create these mechanisms that can kind of create a decision pipeline also, where to do these different decision points and the infrastructure that the infrastructure can ultimately perform, right? And this is a perspective that we currently typically don't have, because we actually assume that we have a fixed topology of the building blocks of the infrastructure. And I think that this is increasingly becoming a challenge for us.
All right, so I have unmuted both Drithiman, who asked this question, in case you want to follow up. And otherwise, we can move on with Adele Tusi.
Hi, Schahram. How are you?
Hi, how are you, Adele? Nice to see you.
Good. This is Adele from Monash. Thank you for your interesting talk. My question was about that elasticity and osmotic model you introduced. You know, as we know, we need a management and orchestration layer to manage and orchestrate or monitor the entire ecosystem you are talking about. And the overall idea looks very interesting, but considering the scale of such system, when we are talking about designing such layer in a decentralized fashion, I think designing that mono layer itself becomes so complex that maybe even tougher than the system itself. So the question is that, first of all, what do you think about that? And the other thing is that who should do that for us? Is it different vendors or group of vendors? And what do you think about the role of 5G in that scope?
Yeah, that's a very good question, Adele. I think that we are responsible for doing that. I think most of all, this is a question which is much more related to research than the traditional vendor specific perspective, because we as the researchers, we have a kind of a non-biased perspective on the whole infrastructure. We don't have particular interests, right? In a sense, right? So we can actually look at this whole compute continuum and go beyond the borders of these different parts of the infrastructure. You are right that this is a very difficult task, but that doesn't mean that we shouldn't try, right? I think that we can try, and I definitely think that we can do better than what we have so far. This would be my hope and my kind of call for collaboration with all of you, in a sense that we have to become better. Otherwise, we run into increasing problems and we cannot fix those problems, because the solution cannot and should not be that we centralize everything on clouds. As you are all aware, centralized clouds, whatever, I mean, even if you call them decentralized and distributed over them, over 5 different places, they are still kind of centralized as far as I'm concerned. And this has tremendous also political consequences. And at that point in stage, I think we can see that everything that we as computer scientists do has tremendous effect also and connections to the political and societal aspects of the world. So I would like to emphasize that, because we have a responsibility. And as you can see that with social media, what is happening and what social media changed for some good, some bad in the world, similarly, the infrastructures that we are creating has the same potential for that and the same potential benefits for that. And I think that the benefits outweigh the difficulty, and we should at least try to bring in some good mechanisms. And you are right, Adele, I think that the coordination and orchestration is fundamental for this type of systems. How we do it, we do have some ideas. I'm collaborating with a number of great colleagues. Massimo is here, Raj, Ranjan, and Omar Rana. I'm working with them on some of these aspects, and we are also looking at this. So it's an effort in the beginnings, I would say. It's definitely not completed. So, but I think, and I want to invite you all to collaborate with us and help us to create something valuable for the community.
Thank you so much. Excuse me, and what do you think about 5G? Yeah, 5G efforts in that.
Yeah. So I think, as I said, so if you look at the continuum, 5G is one part, or it's basically, it's not the 5G itself. I think this is all great. I think the question actually is on a different abstraction. The question is, do the telcos understand the ecosystem perspective? I have serious doubts because
yeah, I have that problem with 5G. You know, I'm thinking, so what 5G is doing is not exactly what we require.
Yeah, so the problem with the telcos is that they actually even missed the cloud game, right? They didn't fully comprehend what is necessary, and to, you know, they didn't understand the business implications, etc. So the question is, do they understand that there is a place, a potential place for them in this whole thing? I don't know. Nobody really knows. There are some hopes, I think. But I would say that this is probably one of the last few chances. If they get it and become part of this, this is okay. If they don't get it, I think what will happen is that the IT companies will go downstream as the Google and Amazon and Microsoft, etc. are doing. And we will see increasingly mergers and acquisitions of IT companies acquiring telcos. I mean, it easily conceivable that, I don't know, Google acquires some telco, and then life goes on, right? And you can imagine what that might mean, right?
Thank you so much.
Thank you, Adel.
All right, so from Mohammed Sarkaya, we have the question, where should fog data centers be deployed? Latency is a big issue, in particular for real-time processing.
Yeah, so I think the question is still, the solution to this is still open. It depends. It's also related to the question of Adel about this 5G and base stations and the role of the telcos and how the business models evolve. It could be conceivable that if the telcos operate on that level, that they could be operated by the telcos. So some devices managed by telcos, etc. If that doesn't work, maybe we see the rise of some providers, special types of service providers, which show up and provide such services.
And then we have a question from Mohammed Aslampur. Thank you, Schahram. Regarding elasticity in edge and its main aspects, resource, cost, and quality, would you consider serverless computing, as I see you have experience on it? And if so, why does serverless adaptation to edge seem so slow?
That's a very good question. Definitely serverless has a big role to play, but the jury is still out there. I think we have to see not only the, let's say, technical computational models, but also I think it's predominantly a business model game as well. And this seems to be a little bit unclear. How the business models can be and are related to this on a large scale. So that's why I think the progress is a little bit slower.
So I do have also a couple of questions myself I'd like to ask. So first, thank you very much. That was a great talk. One of the questions is, there is sometimes a lot of resistance in the community when you propose things which are bio-inspired or chemically inspired. You know, you talked about resilience and robustness. You talk about the human body and ecosystems. But you do find a lot of resistance in computer science people to follow this kind of paradigm in computing. Have you found that resistance in your and what do you say to that?
Yeah, Carlos, thanks for this observation. I think this is a very wise observation, and you're exactly right. This is exactly what happens. But I also would like to emphasize that we as people, we should not be aggressive against ourselves. We are part of nature. So, I mean, this very principle is also reflected in the autonomic nervous system, which is an example par excellence for an ecosystem, and it is within us. How can we be against? I mean, I see in the world that we are against ourselves, right? This is actually happening. But I think from a world perspective, from the information systems perspective, I think we should, I'm not saying that, you know, we are now, I think I'm not overdoing this bio-inspired kind of thing. I'm using those as metaphors to actually bring across the points, but you're absolutely right. I also observe that there are some resistance. I mean, there's, for example, one aspect I'm working on also for many, many years is the people aspect. People are part of the system. I didn't actually emphasize this in this talk, but if you look at the abstraction and kind of under quotes programming people into such systems and the role of the people have in such systems, it is actually very delicate. And people immediately go into resistance and say, okay, you cannot kind of augment and program people and their interactions, right? But on the other hand, if you don't kind of build better ways to automate and bring in the people, we just end up with social media and email as the ultimate abstraction of human collaboration. And I think that's, we can do better than that. So if you have any other abstraction that helps to bring across the point, I would love to hear it. But Carlos, that's a very good observation. Thanks for that.
And then one last question I had was on this. I'd like to ask about this notion of syntropy or entropy resistance. I thought that was also quite interesting. How do you see that playing a role in this edge intelligence?
Yeah, I think that, you know, this concept of entropy is dominated by physics, as you know. Syntropy is a concept which has come also from systems sciences, etc., which is the opposite effect. And for many researchers, this is a kind of, let's say, an esoteric concept. But in reality, it is what we always do, right? So very simply, as humans, if you don't do sports, if you eat unhealthy, etc., you speed up your entropy. And if you do sports and eat healthy, you are actually doing something for syntropy. And similarly, the question in the systems world is related to software maintenance, software evolution, and stuff like that. So the question is really, can these concepts that we are talking about here now help us to create systems which evolve better, which have less maintenance, etc.? So I think that those are interesting questions, and I think that the concept should be measured against those criteria as well. Ultimately, I think we are still not there yet, but of course that's where we want to go.
All right, so Raj, I don't know if we have time for one more question, or should we move on? It's
yeah, we do have. Are there any questions, or do you want me to ask?
Well, there is a question here. Kunal Rao is asking: applications today are built as microservices. Quality, cost, and resource elasticity you mentioned apply to each microservice individually. How do you see we apply these techniques to the application as a whole as we deploy in the continuum?
Right. So we have a research project which we do with FutureWay in the US, in Silicon Valley, and in that project, which is open source, we are working on that open source, and it's becoming part of the Linux Foundation. Everything that we do, and here we actually create a service level objective kind of abstraction, which allows us to on a higher level attach these things to the services, and then from a user perspective, look at it from a service level objective, which is much more comprehensible for us humans looking at such a thing. Because if you look at it from a microservice level, you don't know if you have more than 5 microservices and having all these things, you have no idea what's going on in the overall system. So we are addressing that with the service level objective, let's say, primitive.
All right, so Raj, please go ahead.
Yeah, just a comment. So thank you very much for nice keynote. You know, I just have a comment regarding that osmotic computing analogy. So you mentioned that from chemistry domain, molecule move from higher concentration to lower. So this is more like comparing, pushing or moving workload from cloud towards fog or edge.
Right.
On the other hand, when we look at IoT application, the data that is sensed near the thing, and the data is actually now triggers certain operation. So of course, with edge computing, we're promoting, yes, let's do something on the device, on the edge. Then whenever necessary, we might push it towards cloud.
Mm-hmm.
So therefore, that analogy of osmotic only holds good for from cloud towards edge, but other way around cannot be.
Yeah, exactly. So these are just abstractions to bring the idea, right? So it's not that it's a one-to-one mapping for sure. That doesn't work. Exactly as you say. The question is, we have to increase this flexibility, this notion of having this understanding that there is an ecosystem, and it has to go from the left to the right and from the right to the left, right? It's a kind of full circle. Exactly.
Great.
Thank you.
Wonderful. So, so thanks again. This is a very nice keynote, and